Okay. Hi guys. Good morning. Good morning all. So I'm Prabhakar. I'm part of MMIR Group 11 assignment, and just I want to explain about this assignment. What is our involvement? This part of assignment is about enterprises knowledge retrieval for pharma and healthcare domain, and especially in pharma we have thousands of research papers, drug labels, clinical trial, and summarizes any physician notes, etc. So we have implemented this healthcare enterprises search engine capable by retrieving a relevant multi-modal documents from healthcare and knowledge base in different phases. So there are phases, and when first phase involved, say, especially to create pre-document processing, like a document pre-processing, like a tokenization, normalization, stopword removal, stemming, and lemmatization. Also, we have created inverted index and positional index, and along with the Boolean retrieval and TF-ID vector retrieval and BM25 ranking, etc. So we have used predominantly Python libraries such as Math, Glob, Asleep, NumPy, Torch, and NLTK. Yeah, that's all my side. Okay, next, Shravani, please go.
Yeah, hi, I'm Shravani, and as part of dense retrieval, we have actually implemented and compared BM25 versus DPR or sentence BERT embeddings, and we performed cosine similarity, dot product retrieval, and top K ranking for them. So, where if when it comes to database, the database that we took is NIH National Institutes of Health Chest X-ray dataset that we took from Kaggle, and that has like more than 30K unique patients and like over 1 lakh chest X-ray scans. So the Python libraries that we used for this were Rank BM25, BM 25 OK API, sklearn feature extraction and extraction text, and TF-IDF vectorizer. So and the other Python libraries were like NLTK library cross encoder and sentence transformers. So BM25 is like it is a widely used keyword based search algorithm that calculates how relevant a document is to a specific search query. Yeah.
Okay, thank you. Krishna, go ahead, please.
Hello, this is Nimegla Krishna. In phase 3, we successfully implemented a high performance two-stage retrieval pipeline to optimize our document search and re-ranking logic. In stage 1, we focus on broad retrieval. We extract the top 50 documents using either BM25 or dense retrieval. As a quick reminder, dense retrieval leverage neural network models to convert text into vector embeddings. This allows us to match queries and documents based on the true semantic meaning and intent rather than just exact keywords. In stage 2, we narrow our focus to precision. We take those top 50 documents and pass them through a cross encoder to re rank them, ensuring the most contextually relevant results bubble up to the very top. To elevate our success, we compared the quality of these 50 documents exactly before and after the re ranking process. The entire pipeline was built using Python, utilizing scikit-learn and TF-IDF vectorizer, alongside the sentence transformers library. Specifically, we used the All-Mini LM LXV2 L6V2 model for generating embeddings and MS Macro Mini LM L6V2 cross encoder for the final re-ranking stage. All right.
Thank you. Next, Anubhav. Sorry, Hanuma, please.
Yes. Hey, I'm Hanuman. So I professionally work on AGTK and production grade, RAG system. So I kind of assumed that this assignment would be a familiar territory. But what I did not expect was how much it is filled in theory underneath the tools that I kind of use day in, day out. So I build retrieval systems for a living, but this is probably the first time that I kind of implemented the guts of one of by hand, and that was the most valuable part of this journey. So what we built was, a healthcare search engine. I would say it is a healthcare enterprise search engine for pharma research. There are thousands of papers, drug labels, summaries of trials, chest X-rays, and someone who needs the right evidence without reading the entire internet first, right? So we built this in 5 phases. The first phase was, classical IR, where we were reading real PubMed articles, tokenized that, stemmed into inverted and positional indexes we built from the scratch. Then with Boolean and TF-IDF and BM25 on top. Phase two added the dense retrieval part where we were using sentence BERT embeddings, which where we try to match the meaning, not just the verbs, plus the NIH chest X-ray dataset, right? Phase three was a two-stage pipeline. We were trying to grab the top 50 candidates fast with BM25 and then re-rank with a cross encoder, right? Now, as the rank person in the room, all the work, all of this is one import statement. You can call a vector DB, call a re-ranker, move on doing it manually. The indexing, the BM25 mathematics, the embeddings finally made me understand why these black boxes behave the way that they actually do. So phase four was all meant, evolution, right? So in the polite way of saying it is, I am the guy, who kind of tries to figure out whether whatever we built is going to work in a shiny demo or is it going to work in production grade system, right? So we kind of implemented everything from precision at the rate K, recall, MAP, MRR, DCG, nothing but with NumPy, partly to understand each one and partly because I have trust issues with anything that kind of hands me perfect score of 100 or 99 in the first attempt itself. So that's a good instinct. So I assumed that the fancy cross encoder would crush everything, but it did not. So plain old BM25 did its magic, even though it was created somewhere in the 80s and 90s. The keyword algorithm quietly built our neural models, the latest neural models in terms of precision and NDCC. The dense models kind of won on MRR, so they kind of kept some dignity there. So my first reaction was the developers of 5 stages in grief, right, saying that I kind of broke the system, but it kind of turned into one of the best finding of the project. Our relevance labels came from PubMed, then our keyword search, of course, the BM25 agreed with that, and they were
Yeah.
like kind of
Okay,
cousins.
Hanuma, just fine. That's
Yeah.
good. I see we
Okay.
exceeded more than 1 minute, but okay, Anubhav,
Okay.
please continue. Thanks, Hanuma.
Yeah.
Yeah. No problem.
So in the phase 5, it was all about multimodal extension. For multimodal, we used text and images and included text from clinical papers and images from radiology scans. So the data set of chest X-ray from NIH, National Institute of Health, was used for this. In this, clip model was used. So one of the models which is very famous is the clip VIT B32. That's a vision transformer model with a 32 cross 32 patch size. Now a clip model is a joint text and embedding model that maps both text descriptions and images into a shared numerical vector space. By doing this, it allowed us to understand how closely a specific image and a piece of an text relate to each other semantically. Uh, so this was the last step of our task,
Yeah,
and
yes.
these are some of the
Yes.
results. Yeah.
Okay, that's good, Anubhav. Thanks, team. Okay, let's stop the recording, please. Thank you.